So when we balance chemical equations, one of the easy ways to start with it is to think of it in terms of an inventory. So if we look at our equation here, we've got hydrogen plus oxygen yielding water. And so we've got hydrogen involved in the reaction, and we've got oxygen, which needs to be balanced out. When we look at an equation like this that shows us the formulas of the substances that are involved, but no coefficients, numbers in front of the formulas, that's known as a skeleton equation. It's a bare bones equation. It tells us what's involved, but not relative amounts. That's important because the law of conservation of matter, the law of conservation of mass, says that you have to conserve and account for every single atom on the reactant side as well as on the product side. So you can't lose or you can't gain any atoms in either direction. So if we start by taking an inventory, we've got 2 hydrogens on the left. We'll write that down, and 2 hydrogens on the right. So right now, hydrogen's balanced. Oxygens, we've got 2 on the left and only 1 on the right. So oxygen's not balanced. So that's where we're going to have to start. So when we look at our equation, the only numbers we're allowed to change are the coefficients, the numbers in front. And once we write the skeleton equation, these formulas are written in stone. You cannot alter them because to do so would alter the substance that you're talking about. So if we want to get a total of 2 oxygens to balance these out, that means we're going to need a total of 2 waters because each water provides 1 oxygen. So 2 waters is going to give us 2 times 1, or 2 oxygens. Now coefficients apply to everything that's in the formula that they come before. So not only does it affect the number of oxygens, it also affects the number of hydrogens. So 2 times 2 updates this to 4, which means we need to come back over here, and now we're going to need a coefficient of 2 in front of H2 to make that 4 hydrogens. And so we've got the same number of hydrogens, same number of oxygens, and so this would be a balanced equation. Next example, nitrogen plus hydrogen yielding ammonia. So we've got 2 elements involved, nitrogen and hydrogen. Okay. And so if we take our inventory, on the left side we have 2 nitrogens and only 1 nitrogen on the right. On the left we have 2 hydrogens and 3 hydrogens on the right. So in this case, both of our elements are out of balance. So now we've got a choice to make. In the previous example, all right, the hydrogens were already balanced. So the only thing to start with was the oxygen. Here we have a choice. And ultimately it really doesn't make a difference which one you start with, because in the end they're all going to be balanced anyway. There are some guidelines that we can watch, that we can keep in mind for some of the larger problems, the ones with more elements in them, that might make things easier to balance. Maybe not if we start with a particular element, but if we leave one for the end, and we'll get to that in the following examples. But in this case, it really doesn't matter which one we choose. Let's just choose nitrogen because it's at the beginning. So 2 on the left, 1 on the right. That means that we're going to need to have 2 ammonia in order to give us 2 nitrogens. Okay? So that updates the nitrogens, but it also changes the number of hydrogens and gives us a total of 6. All right? So now that nitrogens are balanced, we focus on the hydrogens. If we've got 6 on the right, we've only got 2 on the left, so that means we're going to need 3 in front of the hydrogen, which brings that to 6. Both elements are balanced, so we have a balanced equation.